Wah, 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 wah. See what I did there? Nice snag, nice snag. We were at my mother's house one time, and she had cooked us dinner. My wife and 3 kids and I. It was delicious. It was wonderful. And my mom asked the kids and said, "Hey, did you like dinner?" And Teddy said, "No, I like dinner." And I was about ready to crawl under the. I was about ready to smack him upside the head. I was like, "Dude, are you kidding me?" He was like, "I loved dinner." And I was like, "Oh, that's a chip off the old block." All right. Now then, you guys at home should be able to see our 3 warm-ups. And the reason I give you guys warm-up questions is, yeah, to kind of get the ball rolling for class and to give you a way to sort of get your mind right, but also to tie in some things that we may have talked about in a previous lesson, maybe even weeks ago, with the lesson that we're throwing today, the lesson that we're going through today. And so, like, when we talk about evaluating expressions, we're just plugging in a certain number and seeing what shakes out. When we talk about simplifying expressions, we're using order of operations to combine like terms and such. So when we go through these 3 questions, the reason that we're doing it is because in today's lesson, we're going to be using some of these principles like substitution, like combining like terms and things like that. Let's take about another minute. We'll wrap these 3 up. Since I have seen you boys last, I have crashed my bicycle and hurt my shoulder. I don't know if you were aware of Tuesday was our last mountain bike practice, and so the last practice of the year I crashed and burned. It was rough. That's okay. Life moves on. All right. So let's see here. Mr. Wentz going to tell us what to do on number 1. Very good. And one thing that I want you guys to notice is that when we plug in a value like -2 for x, it's really smart to use what? Parentheses. Okay, get into that habit. When you use substitution, do so with parentheses. Okay, do so with parentheses. Joe Edwards, what about number 2? Again, we're asked to evaluate this one is a little bit different. We're not plugging in a number, we're plugging in an expression. So what'd you do here?
I replaced X.
Joe, you're muted, I think. Oh, wait a minute. I bet it's my end. Hold on just a tick. I should have squared this away earlier. Where are we at? Dadgummit. Hold on. I'll be right back. Leave the call. I hate having to do this. Okay. Display audio. All right. Joe, we've all decided that that's your fault. We're going to blame you for this. Can you try and say something now?
I plugged in X for 3A.
All right, good deal. Let me share my screen with you guys again since I left the call so I could go adjust a couple settings, and then it turns out those settings didn't need to be adjusted. Hence the blame falling upon you. But that's okay. Yeah, you're going to plug in 3A for X. And again, we want to get into that habit of using these to do that again. And so there we go. There's the screen right there. Perfect. And so when we do that, what ends up shaking out there, JoJo? So instead of 2x squared, it's 2 times quantity 3a squared. Instead of minus x, it's minus quantity 3a. So in other words, what's 3a quantity squared? What's 3a times 3a?
It'd be 9A
9a
squared.
Squared, good. And I haven't taught you guys about exponents yet, but you should get the idea that 3 times 3 times a, we just say 3 times 3 is 9, a times a is a squared. So in other words, we got 18a squared right here from this first term. And then minus 3a and minus 3. Hopefully that's what you guys got. Just like on number 1, we use parentheses when we plug and chug. And then last but not least, down here on number 3, we're simplifying out, and Jack's going to go ahead and tell us what we should get when we simplify things out. 3x plus 4, easy enough, right? Because we combine like terms. The two x terms go together, and then the two constants come together. And we would just, add the coefficients of those x terms, and there you go. Wham, bam. Thank you, ma'am. Any questions on the warm-up at all? Okay. Pretty easy stuff, hopefully. Now, today's lesson is going to be strange. All right, it's going to be off the beaten path because we're going to be talking about, this notion of what a relation is and a specific type of relation known as a function. There's going to be weird notation. There's going to be some different vocabulary words. So it's not going to be your normal lesson from me so far this year. However, I would venture a guess that there will be some words that we throw out there that you've heard before. There will be some strategies that we employ that you've heard before, okay? So look for those and see if you can snatch hold of them and build upon them, all right? And we'll be all right. So first things first, a relation. What in the dump is a relation? A relation, okay, it's a correspondence between two sets of data, okay? And oftentimes we show that correspondence with a set of ordered pairs, and you're comfy or you're familiar with ordered pairs. And so like looking at example 1, down here, I'll circle it in orange. This is a relation. We are showing the relationship. And in this case, for the first example, we're doing this with ordered pairs. Okay. Now, you have a couple of new vocabulary words, or at least they're new for this year. Have you heard of them before? You guys seen domain and range before? Anybody? A couple of you guys at home are nodding. Anybody here? Shake head, nod head. I don't know. All right. Well, the domain is the set of inputs. Can we write that down? The domain is the set of inputs. Ouch. And the range is a set of outputs. For our normal way of operating, we typically like to use X as our input variable, as our independent variable. And so the set of X values turns out to be our domain, whereas the set of Y values turns out to be our range. Okay, I got a little picture I'm going to show you guys, see if I can look it up easily enough. We were talking about this yesterday with the 9th graders. I used to struggle to remember the difference between domain and range. Okay, so just I'm owning up to that, and the struggle was real when I was in the 8th and 9th grade, and I would forget a lot of things like this. Okay, so I was always on the lookout for little mnemonic devices or things that would help me remember, and so I have a picture to show you. All right. Whoever whoever's got their mic unmuted at home, somebody like with a adult male voice just talked on it. If you guys mute yourself, I got a little feedback coming in from you. I don't know if y'all can recognize this, but does anybody know what the game show it is? The Price is Right. When I was a kid, this fella here in the middle is named Drew Carey. He's the host now, but when I was a kid, it was Bob Barker. Okay, Bob Barker was this old guy. He was probably in his 80s, but he looked like he lived on a beach because he was like spray tan red almost. He was orange, and he had this stark white hair, and he always wore a suit. And he had Bob Barker's Beauties, were these ladies that would come out and help with these pricing games on The Price is Right. It came on 10 o'clock in the morning on Channel 3. Loved watching that all the time. This guy over on the left, can y'all recognize who he is? Snoop Doggy Dogg. All right. And so apparently, when I Googled this several years ago as an illustration of one of those games on that, I found an image, or a video rather, and I just snipped an image of Snoop Dogg helping this guy play the range game. And I mentioned how I would forget which one's which. Had X values domain, Y values range. And so I thought, you know what? I've always watched Price is Right, and they've always done the range game on there. And the way the range game works is that, like, this guy was going to win a car. Okay, so his challenge was to properly price the car. And the way that it would work is that they would start the range game, and this little red thing down here where my mouse is would slowly move up the rangeometer or whatever they call it. Okay, and his job was the audience would be screaming, "Stop, stop!" And so his job was to hit this red button, and it would stop the range. It would stop this little red thing after it had gone up where they thought it was far enough. Because these are all on the left. These are all prices of the car. You know, like maybe it's down here at 20,000, and then up here at the top maybe it's 30,000. So the price of the car is somewhere in that range, and he has to stop it within, you know, like $1,000, let's say. And then Drew Carey would come over here and he'd hit this button, and then the price of the car would show up over here somewhere in this green bar. And if it matched, if the red one matched up with the price, he would win the car. Okay, so that's range game. It goes up and down. What letter have we learned pertains to going up and down? Is it X or Y? It's the Y value. So you'll remember, hopefully, like I did, the range game helps you keep straight that Y values are what we have making up our range, and X values make up our domain. Okay. Oftentimes, I'll use the example of a vending machine as well. You'll hear me talk a little bit later on about a vending machine or even perhaps a factory. And that's a good illustration of domain and range as well. The domain is a set of inputs. Okay, we used to have this ice cream vending machine here at CBHS. Okay, can you imagine an ice cream vending machine? Okay, and it was pretty nifty. You would put your money in, and then it had like this suction arm, this robot suction arm, kind of like the claw. And it would zzz, and it would suck up your, like your strawberry shortcake or your cookies and cream or whatever it was, and it would suck it up, and then it would move it over to the slot, and it would drop it, kind of like the claw machine at the fair. Okay. What you were only allowed to put into that machine was nickels, dimes, quarters, and dollar bills. That was it. And the only thing you were going to get out of that machine was ice cream. You know, maybe like an ice cream sandwich, or like a bomb pop or something like that. So they had a set of allowable inputs. You know, could I put a $5 bill in? No. Could I put a penny in? No. Those two would not be in my domain of that vending machine relation. Okay. Could I get out a plate of spaghetti? No. Could I get out a bowling ball? No. It's because that machine was predefined to only put out certain types of ice creams. So that's a good illustration of domain and range as well. What are you putting in and what are you getting out? Now, looking down here at example 1, it should be therefore pretty straightforward. To state the domain, all we're doing is listing all of the X values in that relation. That's the domain. That's the set of inputs. And the set of outputs, or our Y values, will be 1, 4, 9, 16, and 25. Okay. So the domain and range, identifying domain and range of a function is a very important skill to have. We were talking in the math department meeting a couple days ago about Algebra 2 trig that our sophomores and juniors will take. You guys will probably take that as a sophomore. And how important it is. It's a required skill for them to be able to look at a particular type of relation and say, ooh, I know the domain of that. I could describe the range of that. Okay. So this is what we're working on here today. Hey, could anybody tell me, I talked about how you visualize a relation like this using a set of ordered pairs. There's a lot of ways to visualize it. Another way is with an equation. Okay, could anybody look at this and tell me the equation? Y equals what in terms of x?
Y equals x squared.
Very good. Y equals x squared. And we'll look a little bit later on at how that's a more powerful way of describing a relation between x and y. Because not only now could I talk about the set of data that was provided for me, but I could also answer questions like, okay, what would happen then if I wanted to include an extra point of data? If I wanted to extrapolate the output for x equals 6, and you guys would all tell me what? 36, because you recognize a pattern and because you now have an equation to match that relation, okay? So that's really powerful. I use that word extrapolate. That means when I have a set of data and I want to use that set of data to model the behavior of that relation and then use that model to predict a future behavior or a behavior outside of our data set. That's called extrapolation, okay? If there was going to be interpolation, these are two vocabulary words you should write down. They like to use them on the ACT. If we were going to use interpolation, all right, pretend like that initial set of data was a little bit different. I just scratched out one point, and here we're going to put in the point 6, 36, and we'll pretend like this was our set of data. Okay, so extrapolation is where you take the set of data and you find a missing unknown, outside of the set of data. Interpolation is where you use the data to create your model, and then you find some missing data that might be inside the data set. So in other words, I might say, hey guys, based on this information, what do you think you would get when you have x equals 3? And you'd all say 9. And that would be interpolation. It's pretty much the same process, just two vocab words. Extrapolation and interpolation. A little data analysis there for you. All right, let's talk about birthdays. Let's talk about birthdays, okay? This is a good way to demonstrate or illustrate our third visualization of a relation between inputs and outputs, okay? The first was by a set of ordered pairs. The second, I think maybe Oxley just told us was an equation. Okay. The third, this is called a mapping, a correspondence mapping. Okay. Use that vocab word in your notes, a correspondence mapping. And if you're following along with our homework assignments on deltamath.com, which all of you should be doing, you'll notice that there's an assignment due 3 o'clock on Friday. One of the sets on that exercise list is correspondence mappings. And it's super simple. You've got a set of inputs, that's your domain. You got a set of outputs, that's the range. And then you got some lovely little arrows that are saying, hey, Allison's birthday is April 25th. Penelope, I love that name. Penelope's birthday is May 23rd. June's birthday, ironically enough, not in June, is at August the 2nd. And so on and so forth. This is how we would relate X's to Y's in a very visual fashion. Okay? Now, I ask a couple of hopefully obvious questions in blue and in red. What do you guys think? Nate, can one person have more than one birthday? No, of course not. That's like saying, hey, Allison's birthday is January 12th and April 25th. No, it's not. Okay, that's cuckoo. That does not happen. That is not allowable. We would say no. One input cannot correspond with more than one output in this context. But then you flip the coin over to the other side. Tiago's going to answer our red question for us. Tiago, can multiple people have the same birthday?
Yes.
Yes, of course. Hey, did you get your hair cut, by the way? Looking good, baby. High and tight. I like it. All right, somebody pick me an example from our correspondence mapping of where that second red question gets answered. What do you think there, Reed?
June's birthday and Liz's.
Yeah, June and Liz share a birthday. Stephen and Danny share a birthday. Okay, and that's fine. That's totally fine. All right? So it's okay for a Y value to have two corresponding X values that match with it. It's not okay for the other way around. It's not okay for one X value, to have two corresponding Y values. And we'll talk a little bit more about that here in just a little bit. Okay, here's our second example. I'm really trying to hit you guys up with a lot of different ways to visualize relationships. Okay. We talked about ordered pairs earlier. And so I've got a plot of some ordered pairs. It looks like 6 ordered pairs, right? George, I want you to go through and I want you to pick all of the X values from those 6 ordered pairs and see if you can call them out for me. I'll record them as part of our domain. Fabulous. What'd you do? You just went through and you picked all the X values. That's the domain, isn't it? Okay. Grove, I want you to handle the range, please. Talk to me about all the range values for each of those 6 points.
-3, -1.
Negative. Say that again? Y values. Range has to do with Y values. So for example, what's the, here, let's just pick this one. What's the Y value of that point?
Oh, it's 1.
The Y value, not X value.
Oh, sorry, 5.
Thank you. There we go. Now we're cooking, baby. All right, let me get squared away down here. So we got 5.
3.
All right, hold on. Let me catch up with you. So we got 5. We got 3. Where's there a 3? Right there. Okay, continue. 4. I like that.
-3.
Negative. Huh? Which of these points has -3 as a Y value?
Sorry.
I see -2. Ooh, I see -2 a couple times.
-2 twice.
All right, hold on. -2, -2. All right, so that's everything but this last guy, and what is his Y coordinate? -1. All right, fabulous. Now, I didn't show any particular correspondences there, did I? I didn't show that 0 as an X value corresponds with 3 as a Y value. This is not a correspondence mapping. This is just a plain statement of domain and range having been given, much like with example 1, having been given some ordered pairs, in this case, just graphically speaking, okay? But we can still state the domain and the range. Now, let me ask you, are there any X values that correspond with multiple Y values? In other words, is there an X value that showed up on my domain twice?
Yes.
Yes. And if so, which one? It's -3. Now, I've hinted in the last 2 screens that that's kind of a big deal. That's kind of like saying that George has 2 birthdays. Cuckoo, cuckoo. Doesn't happen that way. -3 had 2 correspondences as far as the range goes. So although this is a relation, this is not a special type of relation that we denote as a function. Let's talk about what a function is, okay? You guys are probably too young to have girlfriends, right? Y'all don't have girlfriends in the 8th grade, do you? Heck, I don't think I had a girlfriend until I was in college. So y'all got plenty of time, but let's talk about girlfriends. Hey, don't take them laugh at me, Jack. I was a late bloomer. All right. Let's talk about the girlfriend relationship as opposed to the marriage relationship. Okay. Mrs. Morgan and I, we once upon a time we were not married. We were dating. Okay. And that relationship was very different than our relationship is now. Okay. Because in order to go from like a dating or a courting relationship to marriage, you got to do certain things. You got to meet certain requirements, don't you? What do you have to do to get married? Y'all know that? George, what do you got to do? Okay, good. So there's got to be a proposal. There's got to be a ring involved always, right? Okay. What else? See, y'all are so young and naive. Read. You got to do some paperwork, right? You can't just romantically say, oh, I love you, let's get married, and then, woohoo, okay, great. Now, there's got to be paperwork involved. Grove? There doesn't technically have to be a first dance, But there are certain things that certain hoops that you have to jump through. The ceremony has to be officiated by someone that has the legal right to do that type of thing, right? You call them maybe a justice of the peace or an ordained minister. There have to be witnesses, right? You got to sign paperwork. You got to get a marriage license or marriage certificate or whatever it is down at the county courthouse usually. Okay, so there's hoops that you have to jump through, and then you're designated, okay, this relation has leveled up to marriage, let's say. So in math, I use that as an analogy because there are relations out the yin-yang between X and Y, but only when you meet certain requirements does that relation become a quote function, okay? A function is a special type of relationship that meets that requirement we've been hinting about. That meets the requirement where every X matches with one and only one Y value. In other words, George can't have 2 birthdays. One X value is only allowed to have one corresponding Y value. Okay? So look at example 3 down here with me, and I want you to help me figure out if the given relation is, in fact, a function. And the way that we're going to do this, very simply put, is we're going to look at each X value. You're going to want to make sure that they don't have another corresponding Y value that's listed somewhere else. So like the X value of -3. Is -3 listed anywhere else in this relation as being matched up with a different Y value? Is it 2 timing negative or 27? It's not. Okay, nowhere else do I have listed -3. Nor do I have listed -2 anywhere else, or -1 anywhere else, or 0 anywhere else. All of these are unique X values. They only have one corresponding Y value, and that's very important. Okay? Now, another part of this notion of being a function is that every Y value, it just has to have at least one corresponding X value. Okay? So like I know 27 is a repeat. 27 applies to a couple of different X values, but that's okay. That's like saying that Liz and Danny both had the same birthday. That's fine. That Y value of 27 can relate to a couple of different X values and no big deal. So we would say that this one, yes, it is a quote function. And the domain would be the set of X values. We've already spent time doing that. -3, -2, -1, 0, 1, 2, and 3. The range will be the set of Y values, which will be 27, 8, 1, 0, 1, 8, 27. That would be the range. Typically, we would not write repeats twice there. Okay. What do you guys think about example 3, part B? All right, some of y'all are shaking your heads. Why not? Why is part B not a function? What do you think, Jack?
9 and 1 both appear twice.
All right, so we got some repeats. 9 is 2 timing. 9 corresponds with both -3 and +3. That's like saying if you watch the World Series, the shortstop Cody Bellinger for the Dodgers has been killing it, right? Mookie Betts, right fielder, has been killing it. That'd be like saying Mookie has more than one number of playoff home runs in his career. That'd be like saying he's got 4 career playoff home runs, and he's got 7 career playoff home runs. It doesn't make sense. That's not a logical thing to say. This is not a function then. It is not a function because, as we said, 9 repeats a couple times, 4 repeats a couple times. You have to have every X matching with exactly one corresponding Y value. Okay, and that's what a function is. Now, we got into this a little bit earlier, and we talked about, and this will be our last slide for today. I got a couple minutes left with you guys. We talked about how one of the more powerful ways of showing a relationship between X and Y is with an equation. Okay, and so I've got 3 equations for you here, and what I want us to quickly do is to figure out which, if any, of these equations are actually functions, where one X corresponds with exactly one Y for the entirety of the relationship. Okay, let's look at this first one, and we'll ask Joey. Joey, can you hear me? Jojo, the circus monkey, can you hear me? Drew Yard? Oh, looks like he might not be able to. Luke, can you hear me? Sublet?
Yes, sir. Yes, sir.
All right, I'll throw it your way, babe. What kind of equation is this we've been studying in this chapter? I'll give you a hint. Starts with an L.
Linear equation.
It's a linear equation. Excellent, fabulous. And Lewis Thomas, can you tell us what form that linear equation is in?
Standard form.
It's in standard form. Very good. So what this means is that if I plug in one x value, okay, like let's say I plug in, let x equal, I don't know, 3, okay? Then that means 2 times 3 plus y equals 7. That's 6 plus y equals 7. Subtract 6 from both sides, that's y equals 1. So there's one corresponding output for that input, okay? And so to test whether or not something is a function, I need to be able to say, yes, that is true, not just for x equals 3, but for all x's. And I'll let the cat out of the bag on this one. It most definitely is. Okay. This linear relation that you guys have been studying about is considered a function because every x matches with exactly one y value. I'm gonna have to cut our lesson off here. You guys, we're out of time. We'll pick up here when we get back tomorrow. And in the meantime, be checking out your homework on deltamath.com. Okay, it's homework section 3.5. It's due tomorrow at 3, and it's real good practice for you guys. We'll pick back up with this lesson tomorrow. Live Jesus in our hearts. All right, thank you very much. And if you're out and about today, you'll be safe on those wet roads.